Morning, students. Audible to you?
Good morning, sir.
Yes, sir.
The last class before your Cat 1 examination. Today's class, I will complete the topic that we started in the last lump system and then solve a couple of problems. Pattern.
Sir, your voice is low.
Okay. So for today's class, the agenda will be to complete the topic that we have started in the last class, the lump systems, and then we'll solve a couple of problems. And finally, I will tell you the pattern for this week's class. This CAT 1 examination. Okay. So where we are we? We have started in the last class, we have started the transient conduction systems. Transient, which means the temperatures keep changing with time. I mean, anything can change with time. We are interested in heat transfer. We are interested in the temperatures changing with time. So that is the transient system, especially when the heat transfer mode is only conduction. And we have seen that there are three categories of this transient systems in conduction. One is the lump system, which is the simplest one, and it has got applications of its own. Then the next we have infinite bodies, and later we have semi-infinite bodies. Okay, so we'll not discuss about infinite and semi-infinite bodies now. We'll see that after the CAT 1 exam. But today we'll talk about the lump systems. So when we say lump system, the first thing that should come to your mind um, is that the temperature inside the object is uniform. That means inside the object, the thermal gradients are absent. So one may ask, what is this? When the thermal gradients are absent, how will actual heat transfer take place? How will conduction take place inside the object? In reality, the thermal gradients are not zero, but the thermal gradients are very small. So such a system is called as a lump system. Now, what is a lump system for one person may not be a lump system for another person if we talk in qualitative terms. Therefore, there is a quantitative way in which we can tell which system is a lump system and which system is not a lump system. So that we shall see in this class. Also, the importance of lump system is that you should try this out in every problem related to transient heat conduction. As I said, transient heat conduction problems can be categorized into three groups: lump systems, infinite bodies, and semi-infinite bodies. So before you try out the procedure of infinite body or the semi-infinite bodies, you should check whether that system is lumped or not. If it happens to be a lumped system, now how to check, I will tell you now. But if it turns out to be a lump system, then consider yourself lucky. The problem has been simplified. It's easy. You have an analytical solution. But if it's not a lump system, then you should either go for a complicated analytical solution, which involves trigonometry and transcendental equations and so on, or you may have to go for numerical solutions, which I skipped in the last class, but we'll take it up again after CAT 1. Or there is what is called as a graphical solution. There are charts made available. So using those charts, we can try to solve such problems. Again, what questions can be asked in any lump system is just like the steady state systems. You will be asked to find out what is the temperature at a particular location, what is the heat transfer, and what is the temperature at a particular time. Now, time also is playing a role because time is another independent variable in the transient system. So, temperature distribution as a function of time, space is important in transient systems, also in lump systems. Okay, so I will project the slides now. So this is what we have seen in the previous class. In the lump system, heat conduction in the absence of the thermal gradients implies infinite conductivity, and because the thermal gradients are absent, we cannot use the conduction equation. See, we have derived the conduction equation in the Cartesian, cylinder and spherical coordinates. That conduction equation cannot be used. Why? Because in that conduction equation, there is a term called dt by dr or dt by dx or dt by dz. That term is becoming zero. That means that conduction equation, the entire left hand side will become zero, which makes it useless. Therefore, that conduction equation, actually the conduction equation itself is derived assuming that there are thermal gradients. But in lump systems, the thermal gradients are absent within the body. Therefore, we cannot use the conduction equation. Therefore, what we did was we resorted to a thermodynamic solution. We used the concept of thermodynamics. We did an energy balance, and using the energy balance and one heat transfer concept at the surface, you see this energy leaving out in the form of convection. We have used this and derived an equation to determine what will be the temperature at any given time. So you look at this equation. This is temperature at an unknown time. T infinity is the temperature of the medium, this medium. Ti is the initial temperature. So T infinity and Ti will be known to us. We should be able to find out what is the temperature at any time. So the time is tau here. So if we substitute the time here in a proper units, and if we know the heat transfer coefficient, surface area, density, volume, and the specific heat of the object, we will be able to tell what is the temperature at a given time. So this is the concept of a lump system. Also, we can find out what is the heat transferred in a given time using this particular equation. We shall see this later. What is this interpretation of this lump system? So based on this equation, you see this, there is an exponent, exp, exponential term. That means the temperature, and look at this Ti minus T infinity. This is the initial temperature difference between the object and the surroundings. Just imagine a hot, hot piece of metal, a solid metal is dropped all of a sudden into cold water. So initial temperature of this hot piece of metal, let us say it is about 1000 degrees Celsius, and the cold water is at 20 degrees Celsius. So initial temperature difference is 1000 minus 20 is 900 degrees Celsius. In the numerator, you have T minus T infinity. That means the actual temperature or the current temperature minus the surrounding temperature. So this is the current temperature difference. This is the initial temperature difference. This ratio of the current temperature difference and initial temperature difference is changing exponentially. That's the meaning. So what is happening? The difference between the solid and the fluid temperatures will decrease exponentially to zero as time approaches infinity. So the solid object and the fluid, the temperature difference between these two will actually gradually reduce. But how long will it take? It will take infinite amount of time, because this exponential term. So that is what is represented in this particular graph. This is the temperature difference ratios. The T minus T infinity is the current temperature difference. Ti minus T infinity is the actual initial temperature difference, and this is the time. And you see, this is how it is changing. It takes a long time to meet to reach 0 degrees difference. Now, one question is that is this lump system valid for all cases of transient systems? No, it has got a limited application. So where is it applied? Where is not? Where is it not applied? So to find that out, let us see this. Imagine this plane wall. This plane wall is subjected to a convective heat transfer on the surface, and the one side of the plane wall is at a temperature Ts1, and other side is at a temperature Ts2, and T infinity is the temperature of the medium, convective medium, and H is the heat transfer rate. Now, if we take a control volume along this, as shown in this dotted line, broken lines, you can say that the heat conducted from this side into this is equal to the heat convected from the control volume to the medium. So Ts1 is greater than Ts2, therefore heat is transferring from the solid to the convective medium. So there is a heat conduction involved and heat convection involved. So if we write the energy balance across this, heat conducted is equal to heat convected. So you see here, heat conducted is a Ka delta T by delta X is equal to HA delta T. So Ka delta T is a TS1 minus TS2. So this one is at a certain instance, at a particular instance. At that time, the heat convected is HA delta T, heat transfer coefficient multiplied by the area. So since this is a plane wall, the area of conduction and area of the convection on both sides is the same. So this A and this A is the same. So TS2 is the surface temperature at this point, minus T infinity is the medium temperature. So heat conducted within the body is equal to the heat convected. Now for this TS1 minus TS2, you see TS1 minus TS2, if this difference is large, then we can say that the thermal gradients are large within the body. If this difference in temperatures is small, then we can say that the thermal gradients are small within the body. So we separate out this temperature ratios, TS1 minus TS2 and TS2 minus T infinity we bring to one side from this equation. So this is kept as this. This one is brought to the left hand side and the remaining terms are taken to the right. So what we have here, L by Ka and 1 by Ha. What is L by Ka? It is familiar ratio, isn't it? L by Ka. That is the conduction resistance. That is within the object, conduction is taking place. Therefore, there is some resistance. That is the conduction resistance. Similarly, 1 by Ha. This is the convection resistance. This is the convection resistance at the surface. So this temperature ratio that you see is a ratio of the conduction and the convection resistances. Now, if you evaluate this, it will turn out to be HL by K. So this A and A will cancel. H will go to the top around the L and K comes to the bottom. So HL by K. So this HL by K is not having any units because you see it is a ratio of two resistances. So these two resistances will have the same units. Therefore, HL by K will have no units. So this term HL by K is called as the Biot number. Bi is the symbol. It is called bio number actually. BIOT is the spelling, but it is pronounced as a bio number with T as a silent. So this bio number is the product of H and L divided by the conductivity K. Now for low Biot numbers, the uniform temperature condition is satisfied. Now you see here, if this Biot number is a large number, much greater than 1, then this TS1 and TS2 are quite different. If this Biot number is equal to 1, the difference between TS1 and TS2 is reducing. But if Biot number is very small compared to 1, then the difference between TS1 and TS2 is also very small. Now, when this difference between TS1 and TS2 is small, we call it as a system where there are no thermal gradients or the thermal gradients are very small. So this concept of lumped system is applicable when the Biot number is very small. Now again, if we simply say very small and leave it, what is very small for me may be different from what is very small for you. So for the practical purposes, people have fixed that value. What is small is 0.1 value. So therefore, lump systems are valid for Biot numbers less than 0.1. So if you calculate the Biot number using this equation HL by K and you find it out to be less than 0.1, then you can treat that particular system as a lumped system. Otherwise, you cannot treat it as a lumped system. So that is the concept of lump system. That is where the lump system is applicable. So as I said at the beginning of this class, whenever you start solving any transient problem, the first thing that you should do is calculate the Biot number. If the Biot number turns out to be less than 0.1, then it becomes a lumped system and you have a equation, simple equation, analytical equation, you can very well solve it. If the Biot number is greater than 0.1, then you are unlucky. The procedure is slightly more elaborate and more complicated. Okay. So remember, any transient system, the first step you have to do is calculate the Biot number to see whether it is a lumped system or not. Now let us take a look at this equation. Biot number, you know that for transient systems, Biot number is important. So what is H? H is the heat transfer coefficient in the medium. K is the thermal conductivity of the solid object. And L is some kind of a dimension. It is the characteristic length. So L is actually L is a ratio of volume and area. So L is also represented as LC, which is called as the characteristic length. Now the characteristic length for different shapes is given here. For a plane wall of dimension 2L. So for example, if this plane wall is there having dimensions 2L, then the characteristic length will be L. So this is calculated using this formula, volume and area ratios. I'll just show you here. Let us say there is a plane wall having a length 2L, and area is, don't consider this area, the side area, that is how the heat transfer is taking place. So the volume of that will be 2L multiplied by A. So for wall, characteristic volume is 2LA divided by the area, total area available is this side and this side, 2A. So this 2A and this will cancel and L will remain. So this is L, characteristic length. Similarly, for a cylinder, if you take cylinder volume is characteristic length is volume. Volume is 5 by 4 T square L, and area is pi dl. Okay, so this pi dl will cancel out with pi L and undo. So what remains is d by 4. D is 2r by 4, or this is r by 2. So for cylinder, it's like this. Similarly, for sphere, you can use the volume of the sphere and area of the sphere and calculate. You will see that for sphere, this characteristic length is r by 3. Okay, so this is what you need to substitute in place of L. Now there is another non-dimensional number called as the Fourier number. Let us see what it is. Now just look at this equation. This is nothing new. This is the same equation as we have seen earlier. So this is the ratio of temperatures, exponent of minus HA by rho Vc tau. So temperature difference ratios, exponents of minus HAS rho divided by rho Vc and multiplied by tau. The characteristic length is volume divided by the surface area. So this is what we used here to calculate the characteristic length. So if you substitute this, now you will take the term inside the bracket, HAS by rho Vc tau. In that A by V, look at this A by V. A divided by V is 1 by LC. So in place of A by V, I see 1 by LC. So H and tau as it is, rho C as it is, and in place of A by V, 1 by LC is substituted. Now this is this particular term is broken up into small fractions for the sake of convenience. So firstly, this is written as HLC by K. HLC by K. HL by K. We have seen what that was here. HL by K is the Biot number. So that's why it is written like this. HL by K multiplied by K by rho C. Do you recognize this term K by rho C? K divided by rho C. Conductivity, density, rho is density, C is the specific heat. K divided by rho C is what is called as the thermal diffusivity. The symbol is alpha. So this is Biot number, this is alpha, and this is tau by LC square. So this is HLC, and in place of K by rho C, alpha is written, alpha tau by LC square. Okay. So this HLC by K is Bio, and this one alpha T by LC square is the Fourier number, is written as a Fourier number. So Fourier number is actually alpha T by LC square. So Fourier number is something that contains the thermal diffusivity, the time, and also the characteristic length. Therefore, this Fourier number is also called as a non-dimensionalized time. So if you try to evaluate the dimensions of this quantity, it is dimensionless. So Fourier number also is a non-dimensional number, but it deals with the time. So it's a non-dimensional form of representing the time. So this term in the brackets is basically a product of Biot and Fourier number. So we will write it like this: t minus t infinity by ti minus t infinity is equal to exponent of minus Biot Fourier. Okay, so this is the concept. Then, so in the lab we have been measuring temperatures, and one of the simplest and cheapest way of measuring the temperature and also practically accurate method is using a thermocouple. So here the quickness at which a thermocouple responds to a change in temperature is called as the response time of a thermocouple, and that is important because we all want the temperatures to be read very quickly. Remember when you were measuring your body temperature using a mercury in glass thermometer, you keep that thermometer bulb under your tongue, and it will take some time. Why that time is taken is because the bulb containing mercury should attain the temperature same as that of your core body temperature. It will take some time for that. So that time is the waiting time. So you will have to wait till the temperature is in equilibrium. The body and the bulb temperature are in equilibrium, are in thermal equilibrium. So that is called as the response time. Similarly, thermocouple is a device which it is used to measure the temperature. It will also have a response time. We prefer that response time to be as slow as possible, because whenever we are trying to measure the temperatures of a medium which is changing, temperature is changing rapidly, then our response time also, the thermocouple also should be able to read the rapidly changing temperature. So that response time should be quick. So it should be able to read the temperatures faster. So this response time again of a thermocouple is depending on the concept of a lump system. If you have seen a thermocouple basically is formed by joining two wires of different materials, and they are joined at this point. This is called as the bead. This bead of the thermocouple is is supposed to be as small as possible. So it's a spear. It's a spear of very small diameter. So we'll see how this influences the response of a thermocouple. A thermocouple should rapidly attain the temperature of the system it is measuring. So the response time is the time taken to reach the thermal equilibrium. So for rapid response, the term rho Vc by Ha. You see this term rho Vc by Ha. So inverse of this. So that must be small, and this can be achieved by small diameter, low density, low Cp, and high. So this term must be small. So to keep this small, we need a small diameter so that the area is small. We need to keep this small. Therefore, area must be large, or this volume to area ratio must be small. In the denominator, we have H, so heat transfer coefficient must be large, and the density must be small, and also the heat capacity must be small. So if we choose materials in such a way, then the response time will be low. So this can be achieved by these conditions. Rho Vc, this term is called as the time constant, or the time constant of the thermocouple. If this time is equal to the time constant, so tau is equal to rho Vc by HAS. Then if you substitute that condition in the equation of the lump system, that means in place of HAS by rho Vc, if we substitute tau, it will become, this expression will become ext minus tau by tau. So minus tau, and this term is 1 by tau. So minus tau by tau is exponent of minus 1. So if you evaluate this exponent of minus 1, it will be 0.368. So the temperature difference between the body and the ambient is 36.8% of the initial temperature difference. That means for this given time, the temperature difference between the thermocouple bead and the medium of whose temperature we are trying to measure, that temperature difference is 36.8%. In other words, the temperature difference would be reduced by 63%. That means This is the attained temperature difference, and this is the remaining temperature difference. So this is the unattained temperature difference. So this will be the result when the time response of a thermocouple is, or the time at a time when rho Vc by HAS is equal to tau, then at this time, this will be the amount of attained and unattained temperature differences. So we shall work out a problem on this, then you will understand what exactly this one means. The time required by the thermocouple to reach 63.2% of the initial temperature difference is called as the sensitivity of the thermocouple. Okay, so this tau is called as the sensitivity of the thermocouple, and that can be calculated as rho Vc by HAS. The lower value of the time constant result in a faster response. So we want that tau to be as small as possible so that we achieve the required temperature difference. Most thermocouples have the same rho and Cp. Thermocouple materials are made out of good conductors, so usually copper. Therefore, we have a density and specific heats same. Hence, response time is a function of the wire diameter only. So ultimately, it turns out to be the response time is depending on the wire diameter, and the wire diameter will determine the diameter of this bead. So most thermocouple time is a function of the wire diameter because rho and Cp are practically constant for several thermocouple materials. So most thermocouples have a time constant in the range of 0.04 to 2.5 seconds. So see, thermocouples can be manufactured using different materials. As I show here, you see these are two different wires. These two materials of these two different wires can be changed, and therefore you have a different thermocouple settings, different thermocouple materials. And because of the range of the time constant is 0.04 to 2.5 seconds, depending on the materials chosen. If it's a very good conductor, then 0.04 seconds. If it is a not so good conductor, that range, the time is a 2.5 seconds. So this is the time needed for this thermocouple to give us the 63% of the initial time difference. The thermocouple reading must be taken after 4 times the time constant. That means you should be waiting till we achieve this 4 times of this time constant to take the reading. Why 4 times? Because then only the temperature difference will be close to 100%. Will attain the temperature difference is close to 100%. So at time constant, we would have reached 63%, 63.2% only of the initial temperature difference. But if you wait for 4 times more than this time constant, then you would have achieved almost 100%. So that's why we'll have to be patient and wait before we take the thermocouple reading. Okay. So that's about some theory and applications of thermocouples, of this concept of lumped system. And one of the important application is in the field of temperature measurement using thermocouples. Okay. Now remember, nowadays we are seeing the thermal guns being used all over the public places to measure our skin temperature to see whether we have a fever or not, because that is one of the symptoms of this COVID. Now that temperature measurement is based on radiation, thermal radiation. It's not based on the conduction, because in conduction there should be a physical contact, but in radiation physical contact is not necessary. Therefore, that temperature measurement is different, and whatever concept that we have seen here, the time constant and so on, that doesn't apply to the radiation method of temperature measurement. Okay. Now we will take up one simple problem and try to solve it. Now the equations for this lump system are available in page 66 of heat and mass transfer data book. Okay, so you can open that. There we'll have equations readily available, so you can solve them. Now look at the problem. An aluminum plate, and all the properties are given. Conductivity is 160, density is 2700, Cp is 0.88 kilojoule per kg Kelvin. Of thickness 30 millimeters and at a uniform temperature of 225 degrees Celsius is suddenly immersed at time t is equal to 0. Time t is equal to 0 in a well-stirred fluid at a constant temperature of 25 degrees Celsius. The heat transfer coefficient between the plate and the fluid is 320 watt per meter square Kelvin. Determine the time required for the center of the plate to reach 50 degrees Celsius. So you see here, the initial temperature is 225 degrees Celsius, and this is dropped in a well-stirred fluid, let us say it's water, at 25 degrees Celsius. So obviously this temperature will drop from 225. After a long time, it will reach 25 degrees Celsius. But we are interested in how long it will take to reach 50 degrees Celsius. So this is a very simple but interesting problem. So we would be interested to know how long we will have to wait for that to reach 50 degrees Celsius. So this kind of problems are having applications in heat treatment, material heat treatment. You know, all these materials or metal casting products, they have to be heat treated at a certain temperature. They have to be soaked at a certain temperature for a certain period of time. So we would like to know how long it will take for the entire material to reach a certain temperature, and then how long we'll have to keep it at that temperature. That's the soaking time. So these are the applications for this particular problem. So let's start solving this problem. So we have a let us say a container, and this container we have aluminum slab. So this we are not told whether it's liquid or solid. So liquid or a gas, some fluid, and this also we are told that it is well stirred. So there is a stirrer here, and we are given the initial temperature is 225 degrees Celsius, and 25 degrees Celsius. Okay, and we are also told that this is 30 millimeters. So we are given 2L is equal to 30 or 0.03 meters. We are also given the value of H. H is 320. Okay. So we will use this to calculate this information to calculate the. We are also given K. K is how much? 1. So we will calculate the Biot number first. Biot number is HLC by K. This is also written as HX by K. X or LC characteristic length. So for a slab, this thickness 2L, see somebody is has not turned off their mic. Please turn off your mics. Keep yourself mute. So H is 320. L is, see, I have shown this table here. You can calculate. If the dimension is 2L, the characteristic length is L. So 2L is 0.3, so half of that. So this is 0.03 by 2 divided by K is 160. So if you calculate that, this is 0.03, and this is turning out to be less than 0.1. Remember, for the object to be considered as a lump system, the Biot number should be less than 0.1. So here in this case, it is indeed less than 0.1. Therefore, it is a lump system. Okay. Now, in the lump system, we are asked to find out, in this case, we are asked to find out tau is how much for the temperature to reach what value? 50 degrees Celsius. Tau to reach 50 temperature to reach 50 degrees Celsius, what is the value of tau? So if you turn to page number 66 of the data book, we have all the data here. The equation is given T minus T infinity divided by T naught minus T infinity is equal to exponent of of minus HA by rho V T and tau. Now, this T is known to us. We want this T to be 50. So 50 minus T infinity is how much? 25 divided by T naught. T naught is the initial temperature. This is 225 minus 25 is equal to exponent of minus H is 320. Now, A by V, this is inverse of V by A. So we'll substitute in the denominator. So this is, we'll keep it there. Density is how much? We are given the density of aluminum as a 2790. And specific heat is given as a 0.88. Now, see this, it is 0.88 kilojoule per kg Kelvin. So we'll have to substitute in terms of joules. 0.88 multiplied by 1000. So H is 320, rho is 2790, C is 0.88 multiplied by 10 power 3, and we have V by A. So this A, if you bring it down, V by A is the characteristic length. So that comes in the denominator, and this is, we have seen here, V by A is nothing but L, 0.03 by 2. And this tau. Okay. So you can see here on the left hand side, we have no everything we can calculate. On the right hand side, only the tau is unknown, but this is in the exponent. So what basically we have to do is we have to take logarithm on both sides. If you take logarithm on the left hand side, you will get some number. Take logarithm on the right hand side, this exponent will vanish, and this side will be e power this term, and so on. So you can evaluate that. So quickly calculate and tell me what is tau. Calculate what is tau here. How much is that? So whatever the value of tau you get will be in seconds, and that will be the time taken for this particular aluminum plate to reach 50 degrees Celsius. Now in the problem we are asked, determine the time required for the center of the plate to reach 50 degrees Celsius. Now, since our system is a lump system, it doesn't matter whether it is the center or midway between center or surface or the surface, because the thermal gradients are not there. All throughout the body of the aluminum plate, the temperature will be uniform. If the center is at 50 degrees Celsius, any other point also will be at 50 degrees Celsius only. That is the advantage of having a lump system. So even though here the center is mentioned as 50 degrees Celsius, in the solution, nowhere we have considered the center point, nowhere we considered the location. That is because this is a lump system, and anywhere in the body, the temperature will be the same, center or surface or any point midway. So it doesn't matter. So don't get confused because of this word center, because key to have a lumped system here. So your time, what's the time taken? So you will get the time as 4 minutes. So This turns out to be 239.3 seconds is 4 minutes. Okay. So that's the solution. That's how you can solve this problem. Now we'll move on to the next problem. You see, this is an interesting problem. A person is found dead at 5 p.m. in a room whose temperature is 20 degrees Celsius. The temperature of the body is measured to be 25 degrees Celsius when found, and the heat transfer coefficient is estimated to be 8 watt per meter square Kelvin. Modeling the body as a 30 centimeter diameter, 1.7 meter long cylinder, and using the lump system analysis as a rough approximation, estimate the time of death of the person. You see here again, this is an interesting problem. This is here, there's a dead body. We are asked to consider this dead body as a cylinder with a lump system. Now, as a lump system cylinder, we are given the diameter and the height of the cylinder. So we are given that the current temperature at 5 p.m. at 5 o'clock in the evening, somebody noticed, and the temperature of the body was found to be 20 degrees Celsius. The room temperature, no, room is 20 degrees. The body temperature is 25 degrees Celsius. So we have here T infinity is 20 Celsius. T is 25 degrees Celsius. Okay, when found, and the heat transfer coefficient is estimated to be 8 watt. H is equal to 8, and other details are given. Now, what is the initial temperature? What is the initial temperature in this case? The initial temperature is the temperature at which this person was alive, and for a healthy body, the temperature is supposed to be about 37 degrees Celsius. So you have to take this and substitute in this equation. You see here in this equation, make the substitution. So you know the current temperature 25 degrees Celsius, room temperature 20, initial temperature 37, room temperature 20, and you know everything on the other side except tau. So you have to find out the tau. That means you will get that time taken for the temperature to drop from 37 degrees Celsius to 25 degrees Celsius. So using that time, you back calculate and tell what is the time of death. So I leave that to you for you as an exercise. You complete that problem. We'll go to the next problem. Here, the temperature of a gas stream is measured using a thermocouple. The junction may be approximated as a sphere of 1 millimeter diameter, and conductivity, density, and Cp are given. The heat transfer coefficient between the junction and the gas stream is 500 watts per meter square Kelvin. The heat transfer coefficient is given. How long will it take for the thermocouple to record 99% of the applied temperature difference? Applied temperature difference means the initial temperature difference. So how long will it take for this to attain this 99% of the applied temperature difference? That's the question. Now again, as usual, we'll start with a schematic diagram here. So we have a thermocouple. I'm exaggerating, it will be not as big. So this is the thermocouple. We are given the heat transfer coefficient as 500 watt per meter square Kelvin. T is 8,400 standard units. Cp is 0.4 multiplied by 10 power 3 joule per kg Kelvin. And we have a K as 25. 5 again standard units. Now for this, firstly let us calculate the Biot number. Biot number is Hx by K, and this is a sphere. So for a sphere, the characteristic length is R by 3 or D by 6. Okay, so H is 500 multiplied by the diameter. What is the diameter? So 1 into 10 power minus 3 is the diameter in meters divided by 6. So R by 3 or D by 6 divided by K is 25. So if you calculate this, you will get it as 3.3 multiplied by 10 power minus 3. So which is much less than 0.1. Therefore, the system is lumped. So you are lucky. Now the condition also is given saying that the thermocouple, how long will it take for the thermocouple to record 99% of the initial temperature difference? That means you should, if it reaches 100%, then it is almost the same. But 99% is when it is 100%, it is the same temperature difference. But 99% means it is almost the same. So this ratio T minus T infinity divided by T naught minus T infinity is given as 1 minus 0.99. So this is 0.01. So 0.99 is 99%. So this is the unattained temperature difference. So this unattained temperature difference, this ratio is 0.01. So now use the equation given in the data book to calculate. Again, what we are asked here, how long will it take? So again, we need the time. So use this equation T minus T infinity divided by T naught minus T infinity is equal to exponent of minus H A by C V rho tau. Now the left hand side is 0.01 and the right hand side is exponent of minus 500 by Cp is 0.4 into 10 power 3. Multiplied by density is 8,400 and A by V, that is the characteristic length. This is 1 into 10 power minus 3 divided by 6 and tau. So from this, again, when you take logarithms on both sides, you can calculate tau. Tau should turn out 5.16 seconds. Okay. So it will take 5.16 seconds to almost accurately, 99% accuracy, read the temperature. So if you wait for a couple of seconds more, then you will get almost 100% accuracy. So this is an example of the thermocouple response time that we have seen in this class earlier. Okay. So I would like to here and just talk a bit about the CAT examination. Your examination is on Monday, isn't it?
Yes, sir.
Yeah. So we have examination on 3 modules, module 1, 2, and 3. Okay. So in module 1, there are basically you are introduced to the concepts of the 3 modes of heat transfer. You are given the rate equations, the conduction rate equation, also called as the Fourier equation. Convection rate equation is the Newton's law of cooling, and then the radiation equation is the Stefan-Boltzmann equation. Okay, so these are the rate equations. You are told what are the rate equations, and we also solved some problems on what are the modes of heat transfer whenever we are given a certain system. So you will expect that kind of a questions. Also, we solved some problems on the application of this rate equation. So maybe simple problems on that you may expect. From module 2, we have seen one-dimensional heat transfer. You have seen this electrical network theory, composite slabs, and something related to conduction. So that kind of questions you can expect from module number 2. In module number 3, the topics covered are the graphical methods of two-dimensional heat transfer and lump system. So from these 2 topics, you can expect questions. Okay. Mostly problems. So make yourself familiar with the fundamental concepts anyway, and also the problem solving. Whenever you solve a problem, make sure that you draw a schematic diagram and label it completely with all the details given, and try to show what is happening, what kinds of heat transfer is taking place, so on and so forth. So it doesn't have to be a beautiful diagram, but it should be a neat sketch, neat and informative sketch. Okay. So that's what I wanted to tell. Data book, it's always better to have data book handy for properties, because sometimes you may not be given the properties. You may have to refer to the data book for property values. So keep the data book handy. And of course, it's an open book examination. So I think CAT 2 will be in-person examination. You are coming back to the campus, so CAT 2 will be here. But CAT 1, I think this is the open book examination. But normally during the regular, before COVID, CAT 2 used to be the open book examination, right? CAT 1 was a closed book examination. I don't know if there will be a change in policy for coming CAT 2. Let us wait and watch. Okay, so as far as this exam is considered, it's not a difficult test. We have given very simple problems. So try to read the problem carefully and be as detailed as possible in your solution. Okay, all the best. If you have any questions, you can ask. Otherwise, I'll start taking attendance.